A team based at Princeton University has accurately simulated the initial steps of ice formation by applying artificial intelligence (AI) to solving equations that govern the quantum behavior of individual atoms and molecules. This level of accuracy, once thought unreachable due to the amount of computing power it would require, became possible when the researchers incorporated deep neural networks, a form of artificial intelligence, into their methods. The study was published in the journal Proceedings of the National Academy of Sciences. In a sense, this is like a dream come true, said Roberto Car, Princeton's Ralph W. *31 Dornte Professor in Chemistry, who co-pioneered the approach of simulating molecular behaviors based on the underlying quantum laws more than 35 years ago. Our hope then was that eventually we would be able to study systems like this one, but it was not possible without further conceptual development, and that development came via a completely different field, that of artificial intelligence and data science. The ability to model the initial steps The new approach enables the researchers to track the activity of hundreds of thousands of atoms over time periods that are thousands of times longer, albeit still just fractions of a second, than in early studies. Car co-invented the approach to using underlying quantum mechanical laws to predict the physical movements of atoms and molecules. Once trained, the neural network can calculate the forces between atoms that it has never seen before with quantum mechanical accuracy. This machine learning approach is already in use in everyday applications such as voice recognition and self-driving automobiles. In the case of AI applied to molecular modeling, a major contribution came in 2018 when Princeton graduate student Linfeng Zhang, working with Car and Princeton Professor of Mathematics Weinan E., found a way to apply deep neural networks to modeling quantum mechanical interatomic forces. Using deep potential molecular dynamics, they were able to run simulations of up to 300,000 atoms using significantly less computing power, for much longer timespans than were previously possible. They carried out the simulations on Summit, one of the world's fastest supercomputers, located at Oak Ridge National Laboratory. This work provides one of the best studies of ice nucleation, said Pablo de Benedetti, Princeton's Dean for Research and the Class of 1950 Professor of Engineering and Applied Science, and a co-author of the new study. We've been able to simulate very large systems, which was previously unthinkable for quantum calculations. Currently, climate models obtain estimates of how fast ice nucleates primarily from observations made in laboratory experiments, but these correlations are descriptive, not predictive, and are. In contrast, molecular simulations of the type done in this study can produce simulations that are predictive of future situations, and can estimate ice formation under extreme conditions of temperature and pressure, such as on other planets. The deep potential methodology used in our study will help realize the promise of ab initio molecular dynamics to produce valuable predictions of complex phenomena, such as chemical reactions and the design of new materials, said Athanasios Panagiotopoulos, the Susan Dodd Brown Professor of Chemistry. The fact that we are studying very complex phenomena from the fundamental laws of nature, to me that is very exciting, said Piaggi, the study's first author and a postdoctoral research associate in chemistry at Princeton. Rare events take place over timescales that are longer than the simulation times that can be afforded, even with the help of AI, and specialized techniques are needed to accelerate them. The goal of seeding is to increase the likelihood that water will form ice crystals during the simulation, allowing us to measure the nucleation rate, said Weiss, who is advised by de Benedetti and Panagiotopoulos. We start with the equation that describes how electrons behave, Piaggi said. The magic is that because of some physical principles, the machine is able to extrapolate what happens in a relatively small number of configurations of a small collection of atoms to the countless arrangements of a much bigger system, Car said. When machine learning algorithms started to become popular, a big part of the scientific community was skeptical, because these algorithms are a black box. For Car, it is satisfying to see the work started 3 decades ago come to fruition. The development came via something that was developed in a different field, that of data science and applied mathematics, Car said. Having this kind of cross-interaction between different fields is very important. This work was supported by the U.S. Department of Energy, Grant to 731 SC00193994, and used resources of the Oak Ridge Leadership Computing Facility, Grant to AC0500 Oregon 22725, at the Oak Ridge National Laboratory. Simulations were substantially performed using the Princeton Research computing resources at Princeton University. Pablo Piaggi was supported by an early postdoc. Mobility Fellowship from the Swiss National Science Foundation. Thanks for watching. Please subscribe my channel for more videos.